You have the floor.
All right, thanks. Like Jakob said, I'm from the University of Alabama, so if you're not tired of hearing from us yet, you will be after this presentation. So this is a work that I did together with Dr. Hainan and Dr. Biddle, who have been here the past 2 days, and then an undergrad, Arya. And so the title is Calibrating Car Following Models Using SUMO-in-the-loop and Vehicle Trajectories from Roadside Radar. So why do we want to do this? Well, if you were here last year, we presented a work where we used roadside radars to measure how drivers in our network behaved, and then we tried to actually physically measure the car following model parameters in kind of honestly a naive attempt. And we realized that that didn't work. So going back, taking another year, we designed a pipeline to calibrate SUMO car following models using our roadside radars that we had deployed in the field. So throughout kind of the past couple of days, I think we've heard a lot about car following models. I don't think anyone's actually thrown the equations up there, but this is what they look like. I'll go through quickly. Basically, one of the most common ones is the intelligent driver model. It has a set of parameters, a maximum acceleration that a driver would do, a maximum deceleration, time headway, desired speed, and then a couple other. There's an acceleration exponent parameter as well. Then there's also the Krauss model, which is the default model in SUMO. It similarly has quite a few of the same parameters. And then there's the W99 model, which we implemented based on some feedback from last year's presentation. It's composed of a longer list of equations, so I didn't list it here. So why do we even want to calibrate car following models? Well, one, they're the building block of traffic microsimulation. Two, for us, we always approach traffic simulation from an energy consumption and emission standpoint, and so we know that the way that a vehicle drives is heavily influential in its emissions. So propagating that through to a traffic network, it's also really important. And then car following models describe how a vehicle drives. We also know that calibration is required for model reliability. And in literature, it's frequently talked about that calibration based on aggregate measures. So if you just calibrate to volumes and edge speeds or travel time, it's non-unique, or there's a non-unique solution for the car following model parameters themselves. So literature typically points to the fact that you need to do trajectory-based calibration. And the problem with trajectory-based calibration is you need high-quality trajectories, and it's computationally expensive. But like I said, last year, we kind of showed to ourselves, at least, that we felt it was necessary to do this trajectory-based calibration. So to talk a little bit about the data set that we have, as part of the project that I'm on, we have 6 radars in the field in Tuscaloosa. And so there's actually 3 intersections, one there, and one down here. And these radars overlap. So they give us the opportunity to take the individual tracks from each one of the radars and fuse them together to get the complete picture of a vehicle as it goes through these 3 intersections. The radars record the vehicle position and velocity at roughly 10 hertz. And to do the actual fusion and association, we convert the radar coordinate system into the Frenet or curvilinear coordinate system. So each vehicle is mapped to a lane center line and then some distance from that center line. And this is really powerful for us because it makes predictions quite easy. So even though the field of views do overlap, it's very rare that the radar actually tracks a vehicle all the way through its field of view. So to get the complete picture of a trajectory, we have to make some short-term, like 3 to 4 second prediction of where the vehicle will be, and the curvilinear coordinate system is really powerful for that. And then we do track level fusion, so we consider some history of the vehicle when we decide if we're matching this tracklet to that one, or vice versa. And so here's a video of some of the data. I've exaggerated the length of these vehicles, but yeah, this is real data from the field. We were watching the vehicles go through, and they've been merged from subsequent radars. You could definitely see some issues in it. Vehicles drop frequently, especially in the intersection, just based on the radar geometry. They have a tough time seeing the intersection, so the prediction and then subsequent refining doesn't always work. But for this work, we looked at a 26-hour period. It comes out to over 70,000 trajectories. These don't necessarily mean there's 70,000 vehicles. As you see, like in intersections, sometimes the vehicles are dropped and then re-identified with different IDs. But because we have 70,000 trajectories, there still are a lot of high-quality trajectories in there. and these trajectories contain numerous scenarios. So we're able to observe vehicles queuing at traffic signals, vehicles entering the network somewhere in between, leaving the network, and then as well just normal car following throughout. And just as a note, we will be open sourcing this data set in a soon-to-be submitted paper, and then for future people to use. But yeah, so for car following model calibration, it's really important to identify calibration-worthy trajectories. This is something that's been covered in literature. Basically, you need a trajectory that slows down, speeds up, and has some amount of constant speed driving. Otherwise, there's really no information. So if you just have a trajectory that decelerates, there's no information in that signal for the acceleration parameter, or vice versa. So we went through, we did some filtering to try and identify these sets of good leader-follower pairs. We identified a little over 2,000 of them, and this is what we used for our car following calibration. So the general pipeline is we had those 70,000 roughly vehicles. We do transformation and filtering, like I said, identify the pairs, and then that gets supplied to a genetic algorithm-based optimization, where we take the leader trace, we take the follower trace, and we supply them to a SUMO simulation, where we use Tracy to control the leader. It moves exactly as the leader did in the real world, and then we're analyzing what the follower did, computing the error, and then iterating. And we actually used Facebook's Nevergrad meta optimizer for the optimization algorithm. Each trajectory takes around 40 seconds to optimize. And we parallelized actually at the trajectory level using Ray. So instead of parallelizing the genetic algorithm, we just do that on a single core, but process many of these at the same time. We found that parallelized is better and is ultimately faster. And for our error metric, we used some prior literature where they've identified kind of the optimal, or what they identify as the optimal error metric, which is the normalized root mean squared error of spacing, velocity, and acceleration, if you're confident in your acceleration data. And here's just a short video of what the calibration process looks like. So I added this red dot. That's what the follower did in reality. And then, of course, we're moving the leader vehicle like it actually moved in real life. And then the genetic algorithm is trying to tweak the parameters of the car following model so that the follower follows this red dot as best as possible. So moving on to the results. Been doing okay on time. We can see across the board that calibration significantly reduces the error. So red is the uncalibrated, and this is the error in spacing, velocity, and acceleration. But then these are the two different error functions that we considered, one with acceleration, one without. Across the board, we see that after calibration, the IDM model performs the best, and it's the best fit model for 81% of the vehicles. So there still are some vehicles where the W99 or the Krauss car following model might ultimately fit better after acceleration or after calibration. This is a velocity profile and the position profile of the video that I shared in the last slide. And so by looking at this trace, we can see that, and also in general, and I didn't include this figure, but it's in the paper, of headways, but IDM and Krauss favor shorter headways than W99. All of them favor slightly shorter headways than we observe in the network, but IDM and Krauss especially, and so we see that in the positional data over here. It's really hard to see, sorry about that. I shouldn't have used that gray color, but and it's also apparent in, by default, when the vehicle stopped, IDM and Krauss both accelerate into the stopped vehicle, whereas W99 does a little bit less anyways. Of the default models, we find that W99 performs the best across all the metrics. However, a really interesting behavior did occur when we calibrated W99 without the acceleration term. It developed this extremely jerky velocity profile. And it's also apparent here in the acceleration error when calibrating without the acceleration term. However, when you do add the acceleration term back in, it brings that error down significantly. We also observed that there is a trade-off between spacing accuracy and acceleration. So when you include the acceleration term, the spacing accuracy decreases. So like I said, we always approach this from the view of fuel consumption. So we wanted to analyze like how the calibrated versus uncalibrated models impact fuel consumption estimation. And so to do that, I devised this plot here, as well as further analysis in the paper, but this plot is showing velocity, acceleration, and then this is the median, and then the top line is the 90th percentile of positive accelerations. And so you can see that in the real world, there's this nice curve, right, that kind of follows with tractive power. And then behind, you can see the uncalibrated, again, bad color choice. Then you can see the calibrated parameters over top. And so across the board, you can see some quite different behavior. So IDM kind of out of the box approximates it quite well. Krauss has this high-end acceleration in the uncalibrated model that's quite unrealistic. And then for W99 especially, it's a very unrealistic like flat acceleration curve at high speeds there. And so, yeah, through calibration, we're kind of able to bring the curves more into reality. But because of this overestimation of possible accelerations at high speeds, the default models all tend to overpredict the energy consumption of follower traces when supplied a leader trace. I will caveat that. I don't know that it necessarily applies to simulation as a whole. This is just looking at follower traces when supplied a leader. And these are also a subset of follower traces that undergo acceleration, deceleration, stopping. It's not necessarily representative of the average trajectory in the network. You also see this behavior of the W99 model, that when it's not calibrated with acceleration again, it has this very high and strange acceleration behavior. So after calibrating the 2000 trajectories, we get this distribution of optimal parameters. So here I'm showing the IDM parameters. In the paper, again, there's the similar plots for the other two models. The IDM parameters show a lot of consistency between the two different air metrics, whereas for Krauss and W99, there's more of a difference. When we look at the parameters versus the SUMO default value, so the SUMO default value for a passenger car is in this black line here, we see that acceleration lines up quite nicely, which was, it felt good for us to see that because we've tried to implement values from literature that typically fall around the 1 meter per second, or 1 meter per second squared value, and that never produces realistic simulations for us. It was always the SUMO default that was producing better simulations for us, so it was nice to see it actually emerge in the data. For tau and min gap, we see that drivers tend to prefer a slightly longer headways in our network, and then for min gap, this is dependent really on the length estimate of the vehicles, and so we're using the radar's length estimate, but we have reason to believe there's a fair amount of uncertainty in that. So the min gap itself could be close. The SUMO default could work. We have a little bit more uncertainty in this optimal parameter. Interestingly, the deceleration shows some odd behavior for IDM, or well, I don't know if odd. It's different than the SUMO default. But what we found is if I would have plotted the Krauss optimal deceleration parameters, it would fit quite nicely with the SUMO default, which we think just because the parameters shared between the two models in SUMO, it was probably set to work well for Krauss, and it doesn't necessarily work as well for the IDM model. We also found that we also allowed action step to be calibrated, and so across the board, 0.2 to 0.4 seems to be the best value. And like was just discussed, it's kind of a proxy for reaction time, though not entirely. Another big caveat for our work is we include speed factor in the calibration, which in hindsight was not super smart, just because there's not a lot of speed factor information necessarily in a follower trace. It's limited in its speed by the leader. And so what the value that the optimization tended to converge on was a speed factor of 1.25 roughly, which is quite fast for our network. And it was also a very wide distribution. And so we don't think that really fits our network. So moving on, hope I have time. Yeah. What I just presented was in our SUMO user conference paper. Since then, we've kind of moved to seeing how this applies at the simulation level. So that was just at the trajectory level. We really want to see what we care about is at the simulation level. So we wanted to see, one, do the trajectory calibrated parameter sets create realistic traffic flow in aggregate? And does it matter in the context of fuel consumption estimation? Like I said, this is a preview of an extension to the paper. And so to do that, like I said, that's the question we had. We also wanted to see if we could optimize at an aggregate level. So we have this nice data set of trajectories. We also have traffic demand that comes from detectors in the roads. We have the traffic signal states. We classify the vehicles based on the radar length. Can we take the radar data, aggregate it in some way that's useful for traffic simulation calibration, and then calibrate the car following models using the simulation as a whole? So the way we did this is we investigated two ways. One was a spatio-temporal aggregation method where we bin the network in space and time and then calculate the mean speeds in those bins, and then use that to, well, basically we calculate that on the radar data, and then we calculate that from the SUMO simulation data using the floating car data outputs, and then we get the same exact, basically it's an array, two-dimensional array, and then we can calculate the mean squared error. And then the other way is we create a distribution of the instantaneous accelerations, and then we're able to then, again, analyze what the distribution of instantaneous accelerations were in the traffic simulation, and then we use the KL divergence to analyze how well the distributions fit one another. The simulation distribution fits the real world. And then for optimization, we also consider stochasticity. So we're really calibrating the mean of the car following model parameters. We're holding the variance from the trajectory-based calibration. We showed in a previous paper that the variance is less impactful or not so impactful for fuel consumption, except for the speed factor variance. So we do include the speed factor variance in the calibration itself. And so to consider stochasticity, we run each simulation 10 times and then take the average of the loss across that, and then that's what's passed into our optimizer, and you can see we get a nice loss function, a curve coming down. Yeah, mean parameters. So we investigated several different methods, but in the end converged on kind of our optimal being the mean squared error of the velocity space-time field, and then the KL divergence of the acceleration. In the process of optimizing this metric, we observed this Pareto front, which I think was discussed at some point yesterday. So it definitely exists for the IDM model, and I don't think said that we're just trying to optimize the IDM model at this point. But what we observe is that, yeah, there's some trade-off between accurately modeling the acceleration, so lower is better, and then accurately modeling the mean squared error of the mean speed space-time plots. And you can see that through optimization, we're able to find what we identify as the optimal point. But the IDM model over here performs quite well at the recreating the space-time mean speed plots. But the acceleration behavior is quite different. Krauss does a better job at acceleration, but a worse job at mean speed. And then W99's way off this plot. It doesn't fit on the x-axis for the acceleration behavior, but it does actually do a good job of recreating the mean speed. And then in between here, the correlated sampling is correlated sampling from the optimal parameters that we identified in the trajectory-based calibration. So we consider the correlation between them. And then the marginal PDF method is sampling independently from the best fit distribution of those parameters. And interestingly to us, they don't tend to recreate traffic flow that well in general. No, I skipped over all my talking points. And so another thing that we wanted to investigate was the implication on fuel consumption. So here we normalized so we simulated for an hour, 100 different times, different random seeds, and we look at the total fuel consumption. We normalize by mass because they don't all have the same exact fleet composition due to radar length estimates. So when we normalize by mass, we see that W99 predicts the lowest amount of fuel consumption of the default models. The default Krauss model predicts the most fuel consumption. IDM is right in the middle. And then our combined kind of optimized method right there falls conveniently right in between IDM and Krauss. And actually, if you do a statistical analysis on this, it's not significantly different from a joint distribution of IDM and Krauss. However, it is different in travel time and delay. So it's it's not, the simple fix isn't just simulate it with Krauss, simulate it with IDM, and then you're somewhere in the middle, which would have been convenient. Yeah, and then you also see that the correlated sampling method and the marginal PDF are, again, high fuel consumers. And interestingly, it's nearly a 20% difference that we observe when we simulate with W99 versus Krauss in the median value. And so this all comes to, does it matter? The other research kind of showed that, I mean, number one, fuel consumption is sensitive to volume. If you don't have the volume in your network right, you're not going to be in the right ballpark. Two is fleet composition. So you have to know what kind of vehicles are on the roads. What kind, if you have semi-trucks, if you have, in Alabama, if you have people who've cut off the exhaust on their pickup trucks, they don't have any catalytic converters. And then also it's sensitive to the car flying model and the parameters, but it's also sensitive to the signal control method. And so for us, like, if we want to report to the authorities, like, this signal control method could reduce fuel consumption by X, we want to know that, one, it would be great to have the absolute quantity right, but could we still get the relative quantity right if we don't necessarily know the fleet composition exactly, and if we're doing an okay job of approximating the car flying model? What we find is sort of. So our calibrated method says that if you switch from free traffic signal control, so these don't have any coordination between them, to coordinated control in our 3 intersection corridor, you would estimate that there would be a 2% decrease in total fuel consumption or a 2.5% improvement. However, if you simulate with Krauss, you could say that you get a 6% total decrease in fuel consumption. And this is normalized by controlling for the different vehicle types. Yeah, and that's it. That's my conclusion, I guess. I don't know what the answer is, but yeah.